A more advanced bonding theory than the Lewis theory is the valence bond theory, which introduces the overlap of atomic orbitals to form hybrid orbitals. For example, when the 1s orbital of one hydrogen atom overlaps with the 1s orbital of another hydrogen atom, a sigma bond is formed. All single bonds, regardless of the atom, are all sigma bonds. In the valence bond theory, larger atoms such as carbon, nitrogen, and oxygen must form hybrid orbitals in order for them to form bonds with other atoms. In the Lewis theory, we know that carbon is capable of forming 4 bonds because it has 4 valence electrons. But looking at this orbital diagram here for a carbon atom, 2 of its valence electrons are paired up, whereas the other 2 valence electrons are unpaired, suggesting that carbon is only capable of forming 2 bonds. With this reasoning, carbon would only be able to bond to 2 hydrogen atoms to form CH2. However, CH2 is extremely unstable. According to the valence bond theory, carbon's s and p atomic orbitals must form hybrid orbitals, turning all these electrons into unpaired electrons, each one capable of forming a bond. These hybrid orbitals are known as sp3 hybrid orbitals due to the fact that there's one s orbital and 3 p orbitals that are involved in bonding. With 4 hybrid orbitals, each containing 1 unpaired electron, carbon is capable of forming 4 bonds, which is consistent with the Lewis theory. In valence bond theory, atoms like carbon do not use pure s and pure p orbitals in forming bonds. Instead, atoms use a set of new orbitals called hybrid orbitals. So the valence bond theory basically uses the concept of hybridization, which is the combination of at least 2 atomic orbitals to form the same number of hybrid orbitals, each having the same shape and energy. So what do hybrid orbitals look like? First, you need to remember that an s orbital is spherical in shape, and a p orbital is dumbbell shaped. When you overlap a 2s orbital with 3 2p orbitals, what you get is a total of 4 hybrid orbitals, known as the sp3. An sp3 hybrid orbital looks something like this, in which one of the lobes is much larger than the other. These 4 hybrid orbitals are oriented towards the corners of a tetrahedron and are capable of forming 4 equivalent bonds. Here's a methane molecule with a molecular formula CH4. Each bond in CH4 is formed by the overlap of an sp3 hybrid orbital of carbon with a 1s orbital of hydrogen. And so you can see that every single bond here in CH4 is a single bond, which means that all of these carbon to hydrogen bonds are sigma bonds. Here's practice problem number 29. What orbitals are used to form each of the carbon to carbon and carbon to hydrogen bonds in propane with the molecular formula CH3CH2CH3? How many sigma bonds are present in this molecule? So the very first thing that you want to do here is to draw the Lewis structure for propane. So analyzing the condensed structure for propane, 3 hydrogen atoms are bonded to the first carbon atom, 2 hydrogen atoms on the second carbon atom, and 3 hydrogen atoms on the third carbon. So let's draw the Lewis structure for propane. So we have 3 carbon atoms, 3 hydrogens are bonded on the first carbon, 2 hydrogens on the second carbon, and then 3 hydrogens on the third carbon. And then all carbon atoms are bonded together. According to the valence bond theory, the carbon atoms use sp3 hybrid orbitals to form the bonds, whereas the hydrogen atoms use 1s orbital to form the bonds. The second question here is asking how many sigma bonds are present in this molecule. So if you remember, a sigma bond is basically a single bond. So all you have to do is count the total number of single bonds here, and that would be the total number of sigma bonds. So in this molecule, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So since we have 10 single bonds, there are a total of 10 sigma bonds. Carbon atoms, as well as other nonmetal atoms like oxygen and nitrogen, are also capable of forming other hybrid orbitals. Besides sp3 hybrid orbitals, there are also sp and sp2 hybrid orbitals. When an s orbital and a p orbital overlap, they form a total of 2 sp hybrid orbitals. The remaining unhybridized orbitals can either be empty or partially filled, as we shall see in the next few slides. On the other hand, when one 2s orbital overlaps with two 2p orbitals, they form a total of 3 sp2 hybrid orbitals with one unhybridized p orbital. So as you can see here, when two atomic orbitals form, you get two hybrid orbitals. When three atomic orbitals form, you get a total of 3 hybrid orbitals. So the number of hybrid orbitals basically equals the total number of atomic orbitals that overlap each other. But the point here is that you always get the same total number of orbitals. So for example, you have 3 hybrid orbitals here and 1 unhybridized orbital for a total of 4. Similarly, over here you get 2 hybrid orbitals and 2 unhybridized orbitals for a total of 4 orbitals. Here's an easy way to determine the type of hybrid orbitals that can form, which basically depends on the number of electron groups on the central atom. So if the central atom has 2 electron groups, that means that 2 atomic orbitals will be involved in bonding. Like for example, s and p orbitals, which would form 2 sp hybrid orbitals, 1 s and 1 p. If the central atom has 3 electron groups, then there will be 3 atomic orbitals involved, 1 from the s orbital and 2 of the 2p orbitals, for a total of 3 hybrid orbitals, which is sp2. If the central atom has 4 electron groups, then 4 atomic orbitals will be involved, forming the sp3 hybrid orbitals. So 4 atomic orbitals, 1 s orbital, and 3 p orbitals for a total of 4 orbitals. And this will form 4 sp3 hybrid orbitals. Here's an example for ammonia and water. And here's the Lewis structure for both ammonia and water, just so you can see it a little bit better. The central nitrogen atom contains a total of 4 electron groups. We have 1, 2, 3, and 4. And so because it contains 4 electron groups, the bonds are all sp3 hybridized. Likewise, the central oxygen atom also contains 4 electron groups, 1, 2, 3, and 4, resulting in the formation of sp3 hybridized bonds. So every single one of these bonds here are sp3 hybridized. Same thing for ammonia, NH3. These single bonds are sp3 hybridized. Here's practice problem number 30. What orbitals are used to form each highlighted bond in the following molecule? In what type of orbital do the lone pairs on each oxygen and nitrogen reside? So to answer the first question here, what orbitals are used to form each highlighted bond in the following molecule, we have to count the total number of electron groups on the central atom. So let's say that we pick this oxygen right here as the central atom. And so this oxygen has 2 bonds and 2 lone pairs of electrons. So you can see that this oxygen as a central atom contains a total of 4 electron groups, 1, 2, 3, and 4. And so because it contains 4 electron groups, it will form 4 sp3 hybrid orbitals. All right, so every single one of these bonds is sp3 hybrid or sp3 hybridized. So these electrons over here are also sp3 hybridized, which means that they reside in the sp3 hybrid orbitals, which basically answers question number 2. In what type of orbital do the lone pairs on each oxygen and nitrogen reside? So the lone pairs here in this specific oxygen reside in the sp3 hybrid orbitals. All right, looking at this oxygen right here. So we have oxygen with a bond here and bonded to a hydrogen. So this oxygen also contains a total of 2 lone pairs of electrons, which satisfies the octet rule. Okay, so you have 2, 4, 6, 8 electrons. And so this oxygen contains a total of 4 electron groups as well. So you have 1, 2, 3, and 4. So this contains 4 electron groups, and so therefore it will also be sp3 hybridized. So this bond here is sp3 hybridized, and the 2 lone pairs of electrons reside in the sp3 hybrid orbitals. Now let's look at this nitrogen right here. So this nitrogen has a bond with a hydrogen up top, and then bonded to a carbon here and another carbon here. So that means that this nitrogen has a lone pair of electrons in order to satisfy the octet rule. And so looking at this bond, or looking at the total number of electron groups, this nitrogen central atom has 1, 2, 3, 4 electron groups. And so in that case, the bonds are also sp3 hybridized. And both pairs, unpaired or both non-bonding pairs of electrons here reside in the sp3 hybrid orbitals. So both these bonds right here are sp3 hybridized. So now let's take a look at the hybridization for some simple organic molecules. So the first one here is ethane, and ethane has this chemical formula or molecular formula CH3CH3, and this is the Lewis structure for ethane, and you can see that both carbon atoms are tetrahedral. Right, you can see that they form 109.5 degree angle. And when you look at one of the carbon atoms, you can see that it contains 4 electron groups. So you have 1, 2, 3, and 4. 4 electron groups for this central atom. This second carbon atom also contains 4 electron groups. 1, 2, 3, and 4. So you can see that each carbon atom contains 4 electron groups. So that also means that every single one of these bonds here is sp3 hybridized. So this single bond here is sp3 hybridized. The bond between carbon and hydrogen is also sp3 hybridized. Here's the ball and stick model for the molecule ethane. And you can see that this molecule has 2 carbon atoms that are single bonded to one another, and that each carbon atom has 3 hydrogen atoms that are also single bonded to each carbon atom. And so basically all of these bonds here are single bonds, and every single bond is a sigma bond. And because of the nature of sigma bonds, a bond rotation can occur between 2 carbon atoms. In the later chapters, you'll learn that larger organic molecules containing sigma bonds can have multiple different structural orientations due to their ability to rotate around these sigma bonds. So here's ethylene, which is another example of an organic molecule with the molecular formula CH2CH2. And shown here is the Lewis structure. You can see that each carbon atom has a total of 3 electron groups, which makes each carbon trigonoplanar and sp2 hybridized. So that also means that every single one of these bonds here is sp2 hybridized. And since each carbon atom is sp2 hybridized, 3 atomic orbitals will overlap and form 3 sp2 hybrid orbitals. So again, that's 3 atomic orbitals. So that would be one of the 2s orbital, atomic orbital, and 2 coming from the 2p orbitals. And so again, when they overlap, what you get is sp3 hybrid orbitals. And we have a total of 3 here. So the remaining unhybridized orbital will contain 1 unpaired electron, as shown here. As you can see here, these 3 sp2 hybrid orbitals form the 3 sigma bonds. So we have a sigma bond here forming between the carbon and the hydrogen, another sigma bond here formed between the carbon and the second hydrogen, and another sigma bond here between the carbon atoms. So that's a total of 3 sp2 hybrid orbitals per carbon atom. And these 3 sigma bonds are formed due to the 3 electrons that reside in the sp2 hybrid orbitals. So if you remember, the orbital diagram for one carbon looks something like this. So you have 1, 2, and 3 sp2 hybrid orbitals, and then there's one unhybridized orbital in 2p. So sp2 hybrid orbitals. So we have a total of 1 electron per hybrid orbitals and 1 in the unhybridized orbital. So these electrons in the sp2 hybrid orbitals are the ones involved in the formation of sigma bonds, whereas this electron in the unhybridized 2p orbital is involved in the formation of what they call pi bonds. And pi bonds are present in double bonds. And so as you can see in ethylene, you have a carbon-to-carbon double bond. So in this double bond, you have a sigma bond, a carbon-to-carbon sigma bond, as well as a pi bond, which basically extends above and below the plane, as shown here. So each of the carbon atoms shown here contains 3 sigma bonds and 1 pi bond, in which 1 sigma bond and 1 pi bond are being shared by both carbon atoms. So a single bond contains 1 sigma bond, whereas a double bond contains 1 sigma and 1 pi bond. In ethylene, due to the presence of a pi bond, the rotation about the carbon-carbon double bond is restricted. Bond rotation in ethylene can only happen if the pi bond is broken, which requires a tremendous amount of energy. And here's another organic molecule, acetylene, which contains a triple bond. And as you can see, each carbon atom contains 2 electron groups, 1 and 2, which makes the carbon sp hybridized. And so again, each carbon atom contains 2 atomic orbitals that will overlap with each other. So 2 atomic orbitals, namely an s orbital and a p orbital. So they will form a hybrid orbital, which would be sp hybrid orbitals. And 2 atomic orbitals will form 2 sp hybrid orbitals, as shown here. So the 2 valence electrons of the carbon will reside in the sp hybrid orbitals, whereas the remaining 2 valence electrons will reside in the unhybridized 2p orbitals, as shown here. So these 2 electrons in the sp hybrid orbitals will form 2 sigma bonds, whereas the 2 electrons in the 2p unhybridized orbitals will form 2 pi bonds. So let's take a look. So we have 2 carbon atoms, and these carbon atoms will form a sigma bond. And each carbon atom has two sigma bonds. And so there will be a sigma bond formed between this carbon and this hydrogen, and another sigma bond between this carbon and this hydrogen as well. And then the two electrons here will form the pi bonds, which basically extends above and below the plane, and another one within the plane. So basically you have a pi bond that will form here, and then another pi bond that will form here. So that's what a triple bond is basically. So a triple bond contains one sigma bond and two pi bonds. And here's what a triple bond looks like. Again, a triple bond contains one sigma bond and two pi bonds. So you have a sigma bond that's formed between the two carbon atoms as shown here, and then a pi bond that extends above and below the plane, and then another pi bond that's perpendicular to the other pi bond. So it's shown over here. So this is one pi bond right here, and then the second pi bond that's basically parallel to the plane, and then the sigma bond between the two carbon atoms. So that's a total of 3 bonds, or a triple bond. So here's a table that basically summarizes the hybridization, bond angle, and the types of bonding. So if you have an sp3 hybridized atom, then most likely the bonding that's involved is a sigma bond. If you have an sp2 hybridized atom, then most likely that contains double bond, which consists of one sigma and one pi bond. And an sp hybridized atom will contain a triple bond, which basically consists of one sigma and two pi bonds. Here's practice problem number 31. Determine the hybridization around the highlighted atoms in each molecule. So let's take a look at this first one here. Again, whenever you're determining the hybridization, the very first step is to determine the number of electron groups for that specific atom. So for this carbon right here, it has 3 hydrogens bonded to it and a carbon atom. So that makes this carbon sp3 hybridized. So let's take a closer look. So this carbon right here has 3 hydrogens bonded to it and another carbon atom. So looking at this carbon right here, you can count the number of electron groups. 1, 2, 3, 4. So it has 4 electron groups. So that means that there will be 4 atomic orbitals overlapping. And so 4 atomic orbitals, specifically s and 3 p orbitals. And so the hybrid orbitals that will form would be sp3. So again, the superscript basically indicates the total number of p orbitals. So this is sp3 hybridized. All right, so what about this carbon right here that's highlighted? So this carbon has a triple bond and a single bond to a hydrogen. And so the total number of electron groups for this one is 2. 1, 2. So 2 electron groups, which means that there's going to be 2 atomic orbitals overlapping. 1 s and 1 p. So in that case, this is going to be an sp hybrid orbital, or sp hybridized carbon. All right, so what about this second molecule here? So let's look at this carbon and the nitrogen. So we have carbon that's double bonded to a nitrogen, and this nitrogen has a lone pair and connected to another carbon. And then this carbon atom is connected to two other carbons. And so again, the very first step that you want to do here is to count the total number of electron groups on that specific atom. So for this carbon, we have 1, 2, and 3. So 3 electron groups for this carbon. And then for this nitrogen, we have 1, 2, 3 electron groups as well. And so in that case, for this carbon, well, since both atoms contain 3 electron groups, then they will have the same hybridization. So in that case, it would be sp2 hybridized. All right, so you have 1 s and 2 p orbitals for a total of 3. So both of them will be sp2 hybridized. And for the last molecule here, we have this carbon that's single bonded to hydrogen atoms and then double bonded to a carbon, and this carbon is also double bonded to another carbon. All right, so looking at this first carbon here, it has 1, 2, 3 electron groups. And so this carbon must be sp2 hybridized. And then the second carbon, or the middle carbon here, contains 2 double bonds, and so it contains 2 electron groups, 1 and 2. With 2 electron groups, this must be sp hybridized. And the third question here basically asks what orbitals are used to form the carbon to oxygen double bond. All right, so since this oxygen is sp2 hybridized, that means that it contains 3 sp2 hybrid orbitals. And so the orbitals that are used to form the carbon to oxygen double bond are the sp2 hybrid orbitals. So that would be the answer for C. sp2 hybrid orbitals. And since this is a double bond, that must mean that the unhybridized orbitals are also involved. So that would be one of the 2p unhybridized orbital. So the fourth question here is asking how many sigma bonds are there in this molecule. So sigma bond is present in all types of bonds, whether it's a single bond, double bond, or triple bond. So these bonds contain 1 sigma bond. And so all you have to do is count the total number of lines here. And that would be the total number of sigma bonds. And so you might want to make sure that every carbon at the end of the line has 3 hydrogens connected to it. So we have 3 hydrogens here connected to this carbon, and then you have another carbon here that contains 2 hydrogen atoms. This carbon here contains 1. This carbon also has 1 hydrogen. All right, so I've distributed all of the hydrogen atoms bonded to each carbon. And so all we have to do now is count the total of sigma bonds. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So there's a total of 23 sigma bonds. And then the final question here is asking how many pi bonds are there in this molecule. So again, pi bonds are present in double bonds. So we have 1, 2, 3 double bonds. So that means that we have 3 pi bonds total. So for E, we have 3 pi bonds.